Hello everyone, and thanks to Mr. Chairman. My name is Shiyi Zhang, a master student at Graduate School and Faculty of Information Science and Electrical Engineering, Kyushu University. I'd like to present to you our topic, a robotic electrochemical biosensor based on kinetic electronics technique. And I will divide my presentation into 6 parts. The content includes research background, concept, principle, fabrication method, the result based on experiment, and finally the conclusion. First and foremost, I'd like to explain you our research background, the wearable biosensors. The wearable biosensors and their issues has become a real-time, low-invasive medical key technology next generation. In this case, due to its excellent biocompatibility, the development of flexible sensor materials has also become a hotspot. A biosensor measures biologic components using biomaterials such as enzymes. Here is an example of a blood glucose biosensor. The enzyme is fixed on the electrode. The amount of hydrogen peroxide produced is measured as a current value, and the glucose concentration is evaluated. Researchers around the world have developed a variety of wearable biosensors with various types of soft materials. For example, a contact lens biosensor that detects glucose from tears, and a mouse guard-based biosensor that detects uric acid in saliva, and TEN2-type biosensors for detecting lactic acid and glucose. However, the use of sensors requires the setup and control of professional researchers, which is an urgent problem to be solved in the popularization of wearable biosensors. The problems such as the replacement, reinstallation due to the misalignment, or deterioration because of the body motion have not been solved. In particular, microfabrication has become an essential technology for making electrochemical detection devices. And in our past research, a new monolithic fabrication process for the mass production of soft film robots that are highly compatible with integration circuits was developed and could be used for the fabrication of new kinetic electronics for applications such as active mechanical sensors. By integrating biosensing technology and micro-robot technology, it provides biosensing functions for the next generation of soft robot integrated system, making wearable biosensors more flexible and controllable. And in this study, in order to demonstrate the integrability of biosensors and soft robots, we designed a robotic electrochemical biosensor based on kinetic electronics. Specifically, it is realized by adding a robot actuation function, then activity performs samplings and sensing to the wearable biosensors. The biosensor can realize the flexible movement and high degree of freedom at a specific frequency or displacement distance by controlling the expansion and bending of the bimorph actuator layer. Then about the electrothermal bimorph actuator film robot substrate. In principle, first I will explain why the film bends, since the coefficient of thermal expansion of ordinate polypropylene is larger than that of polyamide, the OPP and PI. The two materials are glued together, heated, and bent towards the PI side, which has a smaller coefficient of thermal expansion, and the OPP-PI bimorph film is placed on a hot plate and observed. A clear bend can be seen when compared at the room temperature of 23 degrees Celsius and heating at 55 degrees Celsius. Then it is sputtered to form a conductive layer of dry heater electrode. To evaluate thermal deformation of bimorph actuator films, the OPP-PI, copy paper, and aluminum foam were employed as a base films to fabricate 5 types of actuators films. It can be expressed as the function of temperature through the following equation. The high-performance PIOPP bimorph actuator film was used as the actuation layer in the film microrobot experiments. The processing of actuator film for developing a microrobot shown in this picture includes, first, loading of base film for forming bimorph actuator film, and cutting the outline of the film robot. Then, AU disposition by sputtering for electrical layer, partly with stencil mask. And finally, PDMS mechanical buffer layer coating and wiring. And this is a design and photograph of a single-joint, single-finger film microrobot formed by this process with PIOPP bimorph actuator film. And about the formation of enzyme-modified electrochemical sensor on film robot. At first, a 3-electrode was formed on the OPP side of the film by the above method, and then glucose enzyme modified sensor was prepared by first forming a carbon paste mediator layer on gold working electrode, and then followed by casting glucose oxidase solution and Nafion solution. To evaluate the basic actuation characteristics of the film microrobot, a single-finger robot was used. To determine the relationship between the film microrobot deformation and applied power, a constant power was applied to the robot film, and the curvature was measured when the film reached a steady state of heat dissipation and heat supply following the start of thermal deformation, and stopped when a constant deformation was observed. The curvature of the film robot showed a linear relationship with the power supplied with a good reproducibility. And to evaluate the robot speed, the frequency response of the robot deformation was measured in the range of 0.125 to 10 Hz. This figure shows the maximum and minimum values of the robot curvature in each circle. And next, about the force generated when a displacement of the robot tip was 0 was measured. This figure shows the force generated by the robot when driving with a 5 voltage PWM power supplied at duty ratios of 0% to 100%. The force generated by a robot increased magnetically with increasing supplied power. And to evaluate the durability of robots, high-count repetitive bending actuation was performed. The results indicated that this simple film could be used for precise bending operation for approximately 8,000 circles. To evaluate the basic actuation characteristics of the film robot, a film robot with enzymatic sensor was used. To determine the relationship between the film robot deformation and supplied power, a constant power was supplied to the film robot and the horizontal deflection was measured. It shows about 15 mm horizontal deflection with 5 voltage supplied power. The enzymatic glucose sensor was characterized from its amplitumetric response to increase hydrogen peroxide and glucose concentrations, and shows a linear response to increase of sample solution in the range of 0 millimolar to 10 millimolar. And finally, in order to explain the application range of film robot and provide more functions for their combination with biosensors, we fabricate multi-degree of freedom robot with various electrode patterns and shapes. about the two-joint single finger with a series heater electrodes can move the robot chip to a point on a plane by hitting two heaters independently, and about the gripper with a pair of opposite fingers can grasp and release an object precisely by manipulating the left and right fingers independently. And we also developed a four-finger array robot and a mobile illuminator robot. In conclusion, we developed a robotic electrochemical biosensor based on kinetic electronics technique by a simple top-down process. The enzymatic electrochemical sensor which formed on film robot showed a highly linear response throughout the 0 millimolar to 10 millimolar concentration range of the sample solution. The developed sensor on film robot showed about 50 millimeter horizontal deflection with 5 voltage power supplied by the bending action of bimorph film. And in our future work, we believe that this technology will lead to important applications in athlete performance, evaluation, and general long-term care. By using this robotic biosensor, it can provide many opportunities and possibilities for personal health, monitoring, treatment, and management. Thank you for your attention.